So here we have a calorimetry problem that involves phase change. The situation is a sample of ice is dropped into warm water that's being held in an aluminum cup. And the first question is, will all the ice melt? So the information we have, I have it summarized here in this diagram. The mass of the ice, I converted it to kilograms because the specific heat that I gave in the problem uses kilograms, so you want to make sure the units match. The starting temperature of the ice is negative 60 degrees Celsius. Here we have the information about the aluminum cup. We got specific heat of aluminum, the mass of the aluminum cup converted to kilograms. We got the water, mass of water, specific heat of water. The aluminum cup and the water start at the same temperature. If the water is sitting in the cup, which it is, you can definitely assume that the aluminum cup and the water share the same temperature. Okay, so a problem like this that involves phase change, what you want to do is draw out this graph of what happens to a substance as heat is added. So as we talked about in class, starting in the solid state, as heat is added, the temperature rises. Temperature goes up, 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 up until you hit the point where the solid begins to melt. And during a phase change, temperature remains constant. So as the ice melts, temperature remains constant at 0. So we have solid plus liquid. Once the last speck of solid has melted, the temperature will continue to rise. So keep in mind here, what's happening on the x-axis. This should say heat added. We're adding heat to the substance. Temperature rises, 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 and then when you reach the boiling point, the substance converts to gas. So we have a phase change, liquid to gas, and then once the last speck of liquid is melted, the temperature rises again once it's all gas. So what I've done here is I've labeled on this graph where the ice starts. The ice is starting at negative 60. It's a negative right there. The starting temperature of the ice is negative 60. Excuse me. The cup and the water are starting at 30, which really should be down here, but I put it up higher just so I have some room here. So this is not, that dot is not completely accurate. 30 would be down here a little more, but we'll just say 30 is right there. So in answering the first question, basically the way I'm going to solve this, so question number 1, is we're going to do 2 calculations, and the answer to these 2 calculations will tell us if all the ice melts. So the first thing we're going to calculate is the energy needed to melt all the ice. Okay, so looking at our graph here, for all the ice to melt, the ice must first warm, right? This would be the ice warming, and then the ice must melt. So this is 2 calculations. So if you have a temperature change, the equation there is Q equals MC delta T. So that's going to be for this part. And then for the phase change, the equation is Q equals ML. All right, so MC delta T, the mass of the ice, is 0.06. Specific heat of ice is 2010 joules per kilogram degree Celsius. And the change in temperature from negative 60 up to 0 is 60. All right, then for the phase change part, the equation for phase change is Q equals ML. The mass of the ice is 0.06. The latent heat of fusion, down here this is latent heat of fusion, up here is latent heat of vaporization. The latent heat of fusion for ice is given right here. It's 334,000 joules per kilogram. All right, so this is going to give us, you take the answer to this, which I actually don't have here. You take the answer to this, which is going to be, I don't know. But what I do know is that you add these two together, so you can punch those into your calculator. Those two added together gives us 27,276 joules. So this is the energy required to melt all the ice. So I'm going to let you guys punch this into your calculator. This one here is the energy to heat the ice up to 0. This one is the energy to have the ice undergo the phase change. Total energy required for those two steps is 27,276 joules. Okay, second calculation. We're going to find the max energy available from the water and the cup. So in other words, if the water and the cup cooled all the way down to 0, in cooling, the cup and the water are releasing energy, losing energy. So the maximum energy available from the cup and the water is the energy that the cup and the water lose in cooling from 30 degrees Celsius down to 0, because cooling to 0 is as far as it can cool. All right, so the way we do this is we're going to go Q equals MC delta T for the cup. We'll say that's for the cup. And we're going to do it for the water. Q equals MC delta T. All right, so for the cup, the mass of the cup is 0.075. The specific heat of aluminum is 900 joules per kilogram degree Celsius. And the change in temperature, if the cup cooled all the way down to 0, which is the most it can cool, it can't cool below 0, the change of temperature would be 30. All right, for the water, the mass of the water is 0.8 kilograms. The specific heat of water is 4,186 joules per kilogram degree Celsius. And for the water, the maximum temperature change as it cools is 30. All right, so this is going to give us two answers. And you add these two answers together. So I'm going to let you guys punch that into your calculator. I didn't make note of what these come out to. But together, they add up to 102,489 joules. Okay, so these two numbers that I have boxed tell us that the ice will melt completely. And the reason I know that is because the energy required to melt the ice is 27,000 joules. The maximum energy we have available from the cup and the water is 102,000 joules. So there's plenty of energy to melt all the ice. So all the ice will in fact melt. Okay, so in the first question, we were asked to find if all of the ice melted. And we found out that there was plenty of energy from the cup and the water to melt all of the ice. So in the second question says if all of the ice melts, which we now know it does, we're going to calculate the final equilibrium temperature reached. So the equilibrium temperature is the final temperature, and that's going to be somewhere in here. So I'm going to put a dot right here on this graph, and then this represents the final temperature right there. So the way we're going to do this is with the idea of calorimetry, which is heat loss equals heat gain. So in this situation where the ice is dropped into the warm water being held in the aluminum cup, the ice will be gaining heat energy, and the aluminum cup and the water will be losing heat energy. So I'm calling the ice object 1, the aluminum cup is object 2, and the water is object 3. So here's the idea. The heat gained by the ice, so I'm going to put that down as positive Q1, positive meaning heat gain, is equal to the heat lost by the aluminum. The aluminum is object 2, plus, so here I'll put this in brackets, plus the heat lost by object 3, which is the water. Okay, so probably the nicer way to put this is heat gained by object 1, the ice, is equal to negative Q2 minus Q3. So that way we just distribute this negative here. So the minus here just indicates that it's a heat loss. The aluminum cup and the water are both losing heat. All right, now the thing to realize is that this heat gain for the ice happens in 3 steps. That's why sketching this graph out is so important. The ice first warms to 0, then the ice melts, and then it warms. So we have 1, 2, 3. This is 3 steps, this positive Q1. All right, so let's plug the equations in. So the 3 steps are going to be M1, specific heat of ice, delta T. So that's this part right here, MC delta T, and I specified specific heat of the ice. All right, plus M1, latent heat of fusion. That's step 2. That's the equation for a phase change from, solid to liquid. Plus M1, specific heat of water, delta T. All right, so that's this 3rd step. So we're still dealing with the mass of the ice, but now the ice has become water, so we want to make sure that we use the specific heat of water. Okay, this delta T right here is going to be 60, right? Because the ice starts at negative 60 and warms to 0. So 60 to 0 is a temperature change of 60. Now this delta T right here, we're going to plug in T final, which we don't know, minus T initial, which is 0 for the ice. Right, so T final right here, we're going to call it just TF for temperature final. And then down here, the starting temperature for this step here is 0. So we end up with temperature final minus 0. Change is always final minus initial. All right, negative Q2. So now we're on to this part of the equation. So again, this positive Q1 was 1, 2, 3 parts. Okay, for Q2, this is just going to be 1 step because the aluminum cup is going to cool to the final temperature. It's going to cool in just 1 step. So this is going to be negative negative M2 specific heat of aluminum delta T. And then that delta T, again, change is always final minus initial. So that's going to be T final minus 30 because the starting temperature of the aluminum was 30. So we're going to plug that in for delta T. All right, then on to Q3. So this will be minus M3 specific heat of water delta T. That delta T will be T final minus 30. Final minus initial. The starting temperature of the water was 30. Okay? All right, so now, let me section this off here. Okay, so now we're going to plug numbers in. So all the data is listed here. M1 is 0.06. The specific heat of ice is listed right here, 2010. So just to make the video a bit quicker, here's what this is going to simplify down to when you punch the numbers in. This is going to be 7,236. That's this. That's M1. That's this part right here. Plus 20,040. That's this part right here. Plus 251.16 T final. That's this part right here. Notice the 0 just went away, because when you distribute that, multiplying by 0 just gives 0. All right, equals, okay, so this part right here is going to become, let's see, what did I do here? This is going to become, so once you plug this in and you distribute, you're going to take M2, you're going to go boom, boom, distribute it. You're going to get negative 67.5 TF plus 2025. So that right there is all of this distributed minus, so I'm running out of room here, minus 3,348.8 TF plus 100,464. That is this part. Again, you're distributing into that. Okay, so then simplifying again, you take all of that, simplify it, you're going to get 3,667.46 TF equals 75,000. That should be 75,213. And solving that for TF gives an answer of 20.5 degrees Celsius. Okay, so I hope this part here was clear. So let me just circle this. So this circle right here is all of this. Because what you have to do is you're going to M2, you're going to distribute this, and that gives that. This right here is this M3 specific heat of water, distribute it there, that gives this. And then the only thing missing is temperature final.